Resonance involves, what's the best way to describe this? So first of all, resonance, it makes a molecule more stable. That's the key. So that's why we look for it. So what are the factors that we talked about so far that lead to a stable arrangement of electrons shared between atoms, or a stable molecule? When we're drawing a Lewis structure for a stable molecule, what do we try to do to make sure that the molecule's stable? What? Right. So the first thing is to look at the octet rule or the noble gas configuration. That's the biggest factor. We just saw that in the last example. We're trying to predict what's going to happen with the aluminum and the fluorine. We want to make sure they have noble gas configurations. So if all my atoms are nonmetals, I have to make their noble gas configurations by sharing. So that's the goal. What was the other thing we talked about last time to make them stable? We're going to talk a lot more about it today. Yeah, we want to have a balanced charge, if possible. And so what you may have found when you were drawing Lewis structures for all the molecules in the lab was that sometimes there's more than one you could draw that had complete octets and complete noble gas configuration. That doesn't mean that those multiple structures that all had noble gas configurations were equally stable and equally likely to exist in nature. So what we're going to do today is we're going to go through and analyze, are these structures balanced in charge? Because if you find one structure is more charge balanced than the other, that one should be the preferred, more stable structure. But there's another factor we're also going to talk about, which is resonance. If a molecule can experience resonance, generally that makes the molecule more stable. So if I draw two Lewis structures, so if I have a formula, something like this, maybe C3H, I'll make it a little bit simpler. No, that's right. C3H. Change this a little bit. C2 H3O minus. So if I have a formula, my goal is to draw a structure that has complete noble gas configurations and balanced charge. If I find there's more than one structure I can draw that has that, then I look to see if there's resonance in one of those structures. That will probably make the structure more stable. That will be the more likely structure to exist. So how do I look for resonance? Well, when we're drawing a Lewis structure, we're still going to use the same steps we used so far. So I'd start with my skeleton, step one of the 6 steps in drawing Lewis structures. So I'd put the carbons together. Let me put this over here a little bit. Put the carbons together. Put the oxygen on one of the carbons, doesn't matter which, because at this point it's symmetrical. Put some hydrogens in. So now you see maybe there's some different options. I could try putting all 3 hydrogens on the same carbon, or I could put 2 hydrogens on one carbon and 1 on the other, or I could put 1 hydrogen on this carbon and 2 on the other. Why do I recognize that I don't want to put 4 hydrogens on this carbon? Right, I don't want to make 5 bonds, right? The whole point is to start by recognizing I want to make noble gas configurations. So when I put my skeleton together, I use that chemical reasoning to make sure that I'm trying to get to the point where I can complete the noble gas configuration. So I'm not just throwing the atoms on randomly at this point, putting the less electronegative elements in the center, putting the more electronegative elements on the outside, putting the hydrogens in last, and making sure I don't go beyond 8 electrons for any of the elements in the period 2. Then I got to count my valence electrons and make sure I put the right number in. Is that step 2? Yeah, step 2. So carbon normally brings in 4 because it's in 4A, but I've got 2 carbons. Hydrogen is in 1A, but I've got 3 of those. And I've got 1 oxygen, which is in 6A, plus I have 1 extra electron because I have 1 extra negative charge on the overall structure. So that adds up to a total of 18. So far in each skeleton, I've used 2, 4, 6, 8, 10. So I've got 8 left. So step 2, count the number of valence electrons you have. Step 3, subtract the ones you've used from the total that you need to put in. Step 4, use the remaining electrons to put on the more electronegative elements first because they attract the electrons more. So the oxygen has an electronegativity of 3.5, carbon is only 2.5. So I also know hydrogen is never going to have more than 2 electrons, right? So each hydrogen, 1 bond, because those 2 electrons from that 1 bond satisfy its noble gas configuration, give it the same number of electrons as a noble gas. So I guarantee some of you are going to put more than 2 electrons on a hydrogen. That's like the biggest mistake or sin you can make in chemistry. It's the most offensive thing you could do to me. So, what? No, don't do it. No. Yeah, so if there's anything you learn, that should be it. If there's only one thing you get, that would be the one thing. So I don't want to put any more electrons on the hydrogen. And so the 8 electrons should go on the more electronegative oxygen first. So I can only put 1, 2, 3, 4, 5, 6 on there before it's full. And it has 8, same number as neon. So I still have 2 more, so then I would put them on another atom that doesn't have 8 yet. And I would do that in each structure. So at this point, how do I look? Do any of these structures stand out as looking more stable than the others? Or maybe a better question would be, do any of them stand out as looking less stable, and I could say this is not a good arrangement for the atoms, it's not likely to exist. Yeah, what's wrong with this third one? Okay, well that's not necessarily a bad thing. So just because one carbon has more atoms bonded to it and the other carbon has fewer, doesn't necessarily mean it's going to be less stable, right? So I want to use these 3 factors to make my judgment. First, looking at the noble gas configuration. That's usually my first one, because if I draw a structure that doesn't have a noble gas configuration, there are some exceptions we'll see a little later to that, but for the most part, excluding those exceptions, if I draw a structure that doesn't have noble gas configurations, it's probably not reasonable. So if my carbons have 5 electrons, I definitely have a big problem. That's impossible. So I don't have that though. I mean, if my carbon has 5 pairs of electrons, that's a big problem. 5 electrons total is also a problem, but it's not impossible. But this carbon has 2, 4, 6, 8. So it has a noble gas configuration. So that's good for that carbon. Going back to the structure on the right, think about the steps for drawing Lewis structures. Once I do step 4 and put my extra electrons around the more electronegative atom, step 5 was, if I still have electrons, I got to put them on the less electronegative atom. And we did that, right? So I still had 2, I put them here or here or here. Well, step 6 says, then look to see if you have noble gas configuration. Because if you don't have enough electrons on one of your inside atoms, it better be attached to an atom with a lone pair so that lone pair can slide in and make a double bond or a triple bond if necessary. So that's the next thing I look for. Can step 6 save my molecule? Because here, this carbon has 2, 4, 6 electrons. It doesn't have enough. This carbon has 2, 4, 6 electrons. It doesn't have enough. And this carbon has 2, 4, 6 electrons. It doesn't have enough. So in each of my structures, I have a carbon that needs more electrons. The only way to fix it, I can't just stick more electrons in because I have to have 18 total valence electrons. So the only way to fix it is to make sure that that carbon in my arrangement is next to an atom that has a lone pair that can slide in and give it 8. This is the problem here. Because this carbon is the carbon that needs more, but it can't get more because the other neighboring atom, all its electrons are involved in sharing. There's no lone pair on this atom that can slide in there and help save that carbon. So that allows me to recognize that this structure is not going to be the one for me. Oops, I crossed out the wrong one. Dang it. Oh, man. Okay, let me redraw that one. Okay. This other one. This one I don't want. The other two are still possibilities because this one can receive electrons from this oxygen. The oxygen should share a second pair with this carbon, and that would give it 2, 4, and then 6, 8 because there'd be 2 pairs there. This one can also do that. But this one I see, it can do that with either the carbon or the oxygen. That is my clue that resonance is a possibility. Okay? So if I draw a Lewis structure, and there's only one way to satisfy the noble gas configuration, there's only one arrangement of the electrons. With this skeleton, as I have it, with the hydrogens all attached to one carbon, with this skeleton, there's only one way to fix this carbon's noble gas configuration. The only way to do it is to slide those electrons in there. And so if I move those electrons in, they'll be here instead. That looks like a fairly decent structure. I've got 2, 4, 6, 8 on the carbon. Got 2, 4, 6, 8 on the oxygen. 2, 4, 6, 8 on this carbon. 2 on each hydrogen. My noble gas configurations are fine. We talked about formal charge. We'll analyze the formal charge and see if that's balanced as well. So those are both factors I got to look at. But I also need to consider resonance, which was what the original question was about. And so when I'm building my structure and I see that there's more than one possible arrangement for the electrons, that tells me that there's going to be resonance. Resonance is the ability for electrons to flow around and move around. That's stabilizing for electrons, right? Think about what electrons are and what they want. Electrons are negative charge. So what do they want? They want to get close to a positive charge. They're attracted to a positive charge. So if I have electrons that are only on one atom, they can only feel an attraction to one positive charge. That's not as good as electrons that are between atoms, because if electrons are between atoms, they can feel an attraction to 2 positive charges. More positive charge to attract them, more stable. That's the whole reason we form bonds. Okay? So the whole reason we're making these structures is to put the electrons in an area where they can attract to atoms. So when I have lone pair electrons that are stuck and can't move, like over here, there's no resonance here. There's only one way to arrange the electrons. They're stuck like this. This is the only way they can make their noble gas configurations is to be stuck in these positions. This lone pair is just stuck on that carbon. It can't move over to the oxygen. Oxygen already has 8. It can't move over here. The carbon already has 8. So when it's stuck on one atom, it can only attract to one nucleus. That's not as stable as if it can move over multiple atoms and attract to more than one nucleus. So when I'm drawing my Lewis structure, when I'm getting close to step 6, if I see that there's more than one way to move the electrons around, then I know there's resonance, because that's what resonance is. Resonance is the ability of electrons to flow between more than one atom. So the resonance here is this lone pair on the carbon, the middle structure, could move in and make a double bond. So that's one possibility. So let me get rid of this structure that we eliminated to create some space. So one possibility to make my Lewis structure here is I can move these electrons in there and make that double bond. So that would make my structure look like this. If I can draw more than one structure that's good, and those structures are only different in the arrangement of the electrons, that's resonance. So here's one structure that's good. If this lone pair moves in, I've got 8 around this carbon, 8 around this carbon, 8 around the oxygen. Great. That's a good structure. But there's another structure that's also good. If instead of moving this lone pair in, I move the oxygen's lone pair in, I would get an alternative. So if I move this lone pair in, I would get a different structure that would look like this. I'd have carbon, carbon. So this lone pair would still be there. My oxygen would have formed a double bond, and I would have a hydrogen here. So I use a double-headed arrow like this to indicate resonance. So these two structures are in resonance. They're both good. I've got 8 electrons now around the carbon, including this lone pair, 8 around this carbon, 8 around the oxygen, including the double bond. That's stabilizing. So this structure is better than this one. So what else do we know about the movement or the behavior of electrons? When electrons are in orbital, what are they doing? When I have electrons in an atom, or even in a bond between atoms, they're in an orbital. When electrons are in an orbital, this is just a 3-dimensional region in space. It's like soupy electron density, right? It can flow. We saw that demo last time. The electrons can move around. So really the electrons are behaving like waves. And as a wave, they are creating areas of high electron probability and areas of low electron probability. So the electrons are not like just sitting there in some location. They're not moving around on a specific orbit or path. They're just behaving as if they're all around this orbital all at once. So if I can create an orbital that extends over multiple atoms because I have multiple ways that these electrons can move over multiple atoms, that's even more stabilizing. So that's really what resonance does. What resonance does is it creates, if you look at multiple structures that exist, and the only difference between the structures is the movement of the electrons, is what we have here. These electrons could be here, or they could move in, push these electrons out to the oxygen, give me the other structure. Then the oxygen electrons could move back in and push this lone pair to the carbon and give me this structure. I could get both structures. When I recognize that that's occurring because I have multiple possibilities for sharing, that's when I know I have resonance. And I also recognize that the real structure, the way this molecule actually looks, is that over the entire area of electron movement from one structure to the next, there's one long orbital that extends over multiple atoms. And the electrons that are moving are in this long orbital. So they behave as if they're over all 3 of those atoms, the 2 carbons and the oxygens at one time. That's extra stabilizing because now they can attract to 3 nuclei at once. because they're in an orbital that extends over 3 different atoms. So that's how resonance is stabilized. So if you're looking for resonance, when you're drawing your Lewis structure, you recognize when you have more than one possibility for sharing electrons. That allows you to create more than one possible Lewis structure. When you realize those 2 Lewis structures, or 3 or 4, how many ever you have, are only different in the positioning of the electrons, and they're both relatively stable, because they both have noble gas configurations, you've got resonance. And it's a very stabilizing force, because when you have resonance, it allows the electrons more freedom. When I have these 2 pairs of electrons spread out over 3 atoms, the electrons can attract to 3 nuclei at once, plus they're in a long orbital, so they can spread out from one another and avoid repulsions more effectively when they're not all stuck in one small orbital just on one atom. Questions about that? How many of you guys need to take organic chemistry? Okay, resonance is going to be your best friend in organic chemistry. It comes into play in, I don't know, 9 out of 10 times you're analyzing what a molecule is going to do. You have to factor in resonance as a possibility. So this is going to keep coming up, not maybe so much, once in a while in general chemistry, but it's going to be consistent throughout organic chemistry. So it's something that may seem weird and abstract at first, but you want to definitely get a lot of practice with it, because you'll really need to nail it effectively if you want to be successful in organic chemistry.